In this video I'm going to go through the questions in the 30s, which is where most of you seem to have problems. It's going to be the longest video. First one about barium hydroxide. You're asked to work out the concentration of hydroxide ions. They give you the mass, they give you the volume, they give you the temperature. Not all of that is relevant, okay? If they're giving me mass, I'm going to start by working out moles. So it's 3.89. You work out the formula mass of barium hydroxide, and I know I've got this many moles in 100 centimeters cubed. If I know the moles and I know the volume, I can work out concentration. So it's moles divided by volume. You'll notice I've gone from 100 centimeters cubed to 0.1 decimeters cubed, and I can work out the concentration. So this is the concentration of barium hydroxide. But you're not asked for the concentration of barium hydroxide, you're specifically asked for the concentration of hydroxide ions. If we look at the formula for barium hydroxide, we can see that there are 2 hydroxide ions for each molecule of barium hydroxide. So now that I know how many barium hydroxides I've got, I'm going to be timesing that by 2, because each barium hydroxide gives me 2 OH ions, and now I've worked out the concentration of hydroxide ions. So the temperature here isn't relevant at all. And the next question, you're asked to calculate the concentration of barium hydroxide. So you're given this information here. Just make sure you're putting the right numbers in the right place. So it's between nitric acid and barium hydroxide. You're told that you've got 25 centimeters cubed of barium hydroxide. You're told you've got this concentration of nitric acid. And you are also told that the titer and the volume for nitric acid is 26.75. So I've just plugged all of those numbers in. I've worked out the moles of nitric acid first by timesing these two numbers together. Using my equation, I was able to work out the ratio, gave me the moles of barium hydroxide, and then I've got moles divided by volume, and this is my concentration of barium hydroxide. The next one, question 31. I'm asked to calculate the minimum volume of hydrochloric acid, and I'm told that I've got this mass of zinc. So I'm going to start off by writing myself an equation. Not zinc, sorry, nickel. I'm going to start off by writing myself an equation. I've got nickel. I'm reacting with hydrochloric acid. Nickel, I don't actually tell you, do they? But nickel has a +2 charge, and they expect you to know that. You do study the transition metals in a later topic, so you will come across that. But the formula then is going to be NiCl2. And you're also forming hydrogen gas. If I go back and balance that equation, I see I've got a 1:2 ratio then between the nickel and the hydrochloric acid. So I have my mass of nickel, I've got my formula mass of nickel, I can work out the moles of nickel. Using my ratio 1:2, I can then work out the number of moles of hydrochloric acid. You're asked to calculate the volume. If I want volume, I can take the number of moles divided by the concentration. So I've got moles, I've got concentration, and that will work out volume. Using this, I will get my volume in decimeters cubed. You're asked for the volume in centimeters cubed, so you'll have to times it by 1000. The next thing it asks is to calculate the volume of H2 in centimeters cubed that will be produced. If you look here, you've got a 1:1 ratio between nickel and hydrogen. So I've got the number of moles of nickel. The number of moles of hydrogen produced will be exactly the same, but I'm not asked for moles, I'm asked for volume. And to go from moles to volume, I times it by 24,000 because I'm asked for centimeters cubed, not decimeters cubed. The next one, I'm not going to lie, this definitely would have caught me out. You're asked if you change from nickel to magnesium, how will it affect the volume of hydrogen? My first instinct was if you were to use the same mass of magnesium, you would have a much greater number of moles than what we had when we used nickel. Magnesium has a smaller relative formula mass, so when I work out the number of moles of magnesium, I would have a greater number than I did in the question above, and therefore I'd be expecting a greater number of moles of hydrogen to be produced. Then I checked the mark scheme and I realised that I'd overlooked something. Okay, so when we're using ratios to predict how much hydrogen is going to be produced, we always have to use the limiting reagent, and they do tell you how many moles of HCl you've got, and you can see that the HCl is what is going to determine the amount of hydrogen being produced. The HCl is the limiting reagent. The magnesium is so far in excess that it's not going to make a difference. So when I'm Working out the amount of hydrogen produced, I'm using the number of moles of HCl because that's my limiting reagent, and the number of moles of HCl is exactly the same in both reactions. Therefore, the volume of hydrogen is not going to change. That's just something to look out for in these questions. Make sure you're always using the limiting reagent when you're predicting the mass or volume of a product. Next one is the back titration. I know there's so much information on this. I'll just do this part of it first, right? You need to be able to write the overall equation, or you're not going to be able to work out your ratio. So you've got a metal. You know it's in the +2 oxidation state. So when you react it with chlorine, it's going to form a compound with the formula MCl2. And because it's a metal and an acid, you're also going to produce hydrogen gas. This is your general equation. They ask you, they break up the back titration for you, and they ask you, the first thing they want to know is how many moles of excess HCl remain after the reaction with the metal. So with these back titrations, you're always starting at the end. You're starting with the titration. So you had an acid, you reacted it with a metal. The acid was in excess, so there was lots of acid left over. And you titrated that leftover acid with NaOH in stage 3. And if I use my titration calculation, I'll be able to work out how much HCl I had in this titration, which is the amount of HCl I had left over after the reaction with the acid. So I'm told that I've got 25 centimetres cubed of the sample from stage 2, which is the sample with HCl in it. So that's my volume of HCl. With the NaOH, okay, this is what you had in your burette. You're going to need to work out the mean titer. So you'll have to work out your 3 titers, and then you're only getting the mean using concordant results. So this one here will work out as 27.3. And this one is going to work out as 27.2, and they will be your concordant titers. Okay, this one is going to be discarded. So once you've got the mean, that's going to be the volume there for NaOH. So you've got the volume of NaOH, you've got the concentration of NaOH here. Timesing those numbers together, you'll work out the moles of NaOH. You've got a 1:1 ratio. So you work out the number of moles of HCl that's left over. Now this is the number of moles that you've got in 25 centimetres cubed, but you can see at the end of stage 1 with the leftover acid, you made it up to 250 centimetres cubed. So you need to work out how many moles you've got in 250 centimetres cubed, and you'll do that by multiplying by 10. So I have this number of moles in 25 centimetres cubed, times it by 10 to scale up. This is the number of moles I've got in 250 centimetres cubed. So this is the number of moles, this is the HCl that you have got left over after you react it with the acid. And if we come back up here, you can work out how much HCl you had at the start. So they tell you the concentration, they tell you the volume. To work out the moles, I'll be timesing these two numbers, but I need to put that into decimeters cubed before I can multiply. So I work out the number of moles of HCl I had at the start. I've already worked out the number of moles of HCl I have left over. So if I take what I had at the start, subtract what I have left over, this is the number of moles of HCl that actually reacted with the metal. And if I know how much HCl reacted with the metal, I can work out how much metal I actually have. So I've got 0.1228 moles of the acid. If I come down here and use my balanced equation, I've got a 2:1 ratio. So divide by 2, I can work out how many moles of the acid I actually had at the start. I know the mass of the acid I had was 6.9, and given that in the question. So the mass of the acid divided by the moles of the acid gives me the formula mass of the acid, and then by looking at my periodic table, I can work out that the metal is cadmium. I didn't do these, you can get from your mark scheme. The next part of this is another calculation question. So a student gets given a carbonate, they don't know what the metal is, and they do this practical to try and work out what it must be. The first thing you're asked is how much CO2 is released. Okay, so you can see here in your equation that you're losing carbon dioxide because it's a gas. You can use these numbers here to figure out how much carbon dioxide must have been lost. So this is before the reaction, the mass of everything, and this is the mass of everything after the CO2 is gone. The difference between the two is the mass of CO2. You're asked for moles of CO2, so it's going to be mass divided by formula mass. That's the number of moles of CO2 that escaped. You're then asked to calculate the molar mass of X2CO3, so that's the MR of X2CO3. To work out the MR, you need moles and you need grams. So if we come back up here, we'll be able to work out grams, okay? This is the mass of the conical flask, the acid, and the X2CO3. This is just the conical flask and the acid. So if I subtract this top number from this middle number, I can work out the mass of X2CO3. So there's my mass, 14.57 grams. So I know the mass. To work out Mr, I also need to know the moles. And if we look at our balanced equation, if I'm getting rid of that many moles of CO2, because there's a 1:1 ratio between CO2 and my carbonate, this must be the number of moles that I started with, 0.0625. So I know mass, I know moles, I can work out formula mass, okay? And remember the formula of it is X2CO3, so this is the formula mass of X2CO3. I can subtract the mass of the carbonate part and then divide by 2 to work out that I must have rubidium. The rest of this I think you can get from your mark scheme. I was asked for 33. So a student is titrating sodium hydroxide with hydrochloric acid and they're getting smaller titer. So remember, the titer refers to what's being added from the burette. You're adding less than everyone else and they want to know why. First thing, burette readings are taken from the top instead of the bottom. That's not going to make a difference, okay? If I'm reading something from the top, all right, say that's at the top, let's say it's 2. At the top of this one, let's say it's 6. The difference between 2 and 6 is 4. And let's say I read it now from the bottom, and at the bottom it's 3, and at the bottom here it was 7. The difference between 3 and 7 is still 4. As long as you're doing it consistently, it's not going to make any difference because you're getting the difference between the two. So that's wrong. The conical flask is turns water. No, that's not going to affect the titer because water cannot react with what's in the conical flask. Therefore, it's not going to affect how much you add from your burette. If an air bubble is released, you're going to end up getting a bigger titer, because just say you have written down that you have added 20 centimeters cubed. In actual fact, you haven't added 20. You might only have added 19, and 1 centimeters cubed was just air bubbles. So that's going to give you a bigger titer because you're not adding as much as you thought you were. But this last one here, that if the pipette is rinsed with water before filling it with NaOH, you're not adding as much NaOH. The NaOH here is in the conical flask. If you've got water in your pipette, you are not adding as many moles of NaOH as you should be. And if you don't have as much NaOH in the conical flask, you won't be adding as much acid from the burette. So you're going to have a smaller titer. Which statement gives the numerical value of Avogadro's constant? So you'll need to work out what the answer to all of these problems is and then see which answer is Avogadro's constant. So the number of moles in 12 grams of carbon-12, if I want to work out moles, it's mass, which is 12, divided by MR is 12. 12 divided by 12 is 1. 1 is not Avogadro's constant, so A is definitely wrong. B, the number of electrons lost by 20.05 grams of calcium. So I need to work out how many moles of calcium I have. So it's going to be 20 divided by 40. So I've just rounded this down a little bit, but it's 20 divided by 40. So you have 0.05 moles of calcium. Then I need to work out how many actual calciums I have. So I do 0.5 times by Avogadro's constant. Now I know how many actual calcium atoms I have. And each calcium will lose 2 electrons. So I multiply by 2. Okay? And if you work out that sum, you should be able to see it here. The 2 by the 0.5 is 1. And 1 times Avogadro's constant equals Avogadro's constant. So I'm thinking here my answer is definitely B, but I'm going to want to confirm. The next one, the number of molecules in 16 grams of oxygen. So to work out the number of molecules, I need number of moles by Avogadro's constant. It's going to be 16 divided by 32. Okay, remember oxygen is O2, so the formula mass of oxygen is 32. So that'll be 16 divided by 32 is a half. A half times Avogadro's constant is a half of Avogadro's constant. So that's incorrect. And then the number of moles in 1 mole of chlorine molecules. You've got 1 mole, sorry, the number of atoms. So if you've got 1 mole of chlorine molecules, it's 1 number of moles times Avogadro's constant. That's how many chlorine molecules you have. But because chlorine is Cl2, you'd have to times it by 2 So you're not going to end up with the numerical value for Avogadro's constant. The answer there is B. Next one, phosphoric acid is a tribasic acid. They want the mass of calcium hydroxide that will neutralize it. So you are told how much phosphoric acid you've got. You're told the volume, which I have put into decimeters cubed, and you're told the concentration. To work out the moles, I times these two numbers. This is the moles of H3PO4 that you've got. You need to work out how much calcium hydroxide is required to neutralize it. So I wrote myself an equation between calcium hydroxide and phosphoric acid. It's a neutralization reaction. You're forming a salt, calcium phosphate. You're also forming water. And when I balance that, I see there's a 2:3 ratio between the two. And to work that out then, it's 0.01 divided by 2 multiplied by 3, and I'll work out in moles how much calcium hydroxide I need. Once I know moles, I times by the formula mass of calcium hydroxide, and I get an answer C. You could get away without writing out the full equation, okay? Because the parts of the molecules that are going to react, they tell you it's tribasic. So you know you've got 3 H pluses, and you can see in the formula here you've got 2 OH minuses. So even without working the whole thing out, you can see that you're going to need how many moles of the hydroxide that you are going to need. The next one, it's a titration calculation, just not with an acid and a base, which makes it this kind of equation I can see being a bit off-putting. But if you read through the information, ultimately you have your sodium thiosulfate, sodium sulfite that we're getting from the burger, and ultimately when you're doing the titration, it's the SO3 2- ions that are involved. And I know it says other stuff, but you're ultimately titrating those ions against potassium manganate. So when I come down here and look at this big equation, which I get is off-putting, the bit that I care about is the manganate. So potassium manganate has MnO4, there's the MnO4. I'm titrating that against SO3 2-. The rest of it isn't going to be relevant. So when I'm writing out my moles table, SO3 2-, and I've got MnO4-. They tell me that I'm going to be using 25 centimeters cubed of the sulfate ion, so that's the volume. For the manganate, they tell me down here 12.6 is my volume there, and they tell me the concentration here. Times these two, I work out the number of moles, and then using my ratio, which is 2:5, I work out the number of moles of the SO3 2- ion. That's the number of moles I've gotten 25 centimeters cubed. I times by 10 to work out how much I've gotten 250 centimeters cubed, because that's the solution is made up till. If I know how many moles I've gotten 250 centimeters cubed, I times by the formula mass of sodium sulfite, and I can work out the mass of sodium sulfite I must have in 250 centimeters cubed. Now they tell me that when I was making up that solution, I was used 525 grams of burger meat. So when I know the mass in 250 centimeters cubed, I know the mass that I got from 525 grams of burger meat. But you're asked if it's safe. They tell you it's okay to have 850 per kilo. So if you've got this number in 525, if I divide by 525, I can work out how many grams of sodium sulfite I have got in 1 gram of burger meat. I times it by 1000 to work out how many grams I've got in 1 kilo of burger meat, and I can see it comes in as less than the recommended amount, so it is safe. The next one, I think this is quite tricky actually. They ask you the empirical formula of the hydrocarbon. So you've got a hydrocarbon CXHY, you're combusting it and you're making CO2 and you're making H2O. And then specifically they tell you you're making 3.38 grams of carbon dioxide. What you're going to have to, usually in these cases you'll work out moles, which is what I initially tried to do, and then I went absolutely nowhere with that. So eventually I figured it out. You've got 3.38 grams of CO2 being produced, and in carbon dioxide, the formula mass I know is 44, and 12 of that 44 comes from carbon, and the rest of the formula mass is coming from the oxygen. So I worked out the percentage by mass of carbon in carbon dioxide by taking the 12 from the carbon divided by the 44, the full formula mass of carbon dioxide, and I worked out that 27% of carbon dioxide is made up of carbon. And all of that carbon must have come from the hydrocarbon. There's nowhere else for that carbon to have come from. So 27% is coming from the hydrocarbon. So I took the 3.38 grams that I know that I formed, and I worked out what 27% of 3.38 was, and I worked out that it was this, and this is the mass in grams that I must have gotten from my hydrocarbon. If I got this much carbon from my hydrocarbon, they tell me I start with a 1 gram, then this is the amount of hydrogen I must have gotten from my hydrocarbon. So I now know the mass of the carbon from my hydrocarbon, the mass of the hydrogen, and once I know the mass of both, I divide by their atomic masses to get the moles, and I simplify the ratio. I get a 1:1 ratio, so it's going to be ACH. You don't have to do this full question, but you should be able to do the percentage yield part, okay? You're trying to make 4 grams of the alkene. You've only got 64% yield. That means you should aim to make more than 4 grams to compensate for what you're going to lose. So I take my 4, I divide by 64, I times it by 100, and instead of aiming to make 4 grams of my alkene, I'm going to aim to make 6.25 grams of my alkene. Once I know how much alkene I'm now aiming to make, I'm just plugging that into a moles table. That's the mass of the alkene I'm trying to make. That's the formula mass of the alkenes. This is the number of moles of alkene. Then this is therefore the number of moles of alcohol I need to start with. That's the formula mass of the alcohol, and 7.9 is the mass of the alcohol I must start with. The other numbers you were given in the question here related to the separation technique. It's not relevant to the calculation that you are doing. And is that it? No, there's one more. Which alkane is 82.8% carbon by mass? You just have to go trial and error on this. So carbon obviously has a mass of 12. In the first one, it's 12 out of a total MR of 16, which is 75%. The next one, you got 2 12s, so you got 24 out of total formula mass of 30, which is 80%. And then the C here, 4 times 12, you've got 48 out of a total of 58, 82.8%, which is what was given in the question. So my answer is C. I don't need to bother to work out D.